The Big Bang theory of the universe's creation has been widely accepted for decades, yet scientists now claim that we are mistaken about both the Big Bang and the cosmos. The cosmos may not have formed exactly as we were taught in textbooks, according to new observations and data. The so-called lithium problem is among the most significant issues. In addition to the matter-antimatter imbalance, it is upending the fundamentals of our cosmology and may pave the way for a whole new way of seeing the world. And incredibly, dense point produced a massive expansion impulse known as the Big Bang. For a long time, at least, it was the dominant opinion. But the James Webb Space Telescope's most recent findings, along with an increasing number of scientific voices, are challenging this notion. Scientists are currently concentrating on the lithium problem. The exact amount of light lithium that should have formed in the initial minutes following the Big Bang is predicted by calculations based on the Big Bang theory. But today, astronomers only find a small portion of the predicted amount when they look for signs of these lithium deposits in very old stars in the JWST data. Before the new space telescope was launched, this paradox was already known, but it is now becoming more and more obvious. Very old stars in the universe that should have displayed signs of lithium concentrations have previously been found by Hubble and other ground-based telescopes, but they haven't had any luck. The numbers did not even roughly match. Even further back in time, the JWST's findings show no elevated lithium levels. Concentrations have been discovered. What does this all add up to, and is the Big Bang theory still viable? The galactic origin of light elements model, or AIM for short, offers another explanation. In this case, lithium is produced by gradual processes in the early generations of stars rather than an initial cosmic fireball. Previous theories suggest that over many millions of years, these early stars contributed the building blocks of life as well as light to the universe. The distribution of matter and antimatter in the universe, or the so-called surface brightness of distant galaxies, is another issue that requires immediate attention. Matter-antimatter dissonance is what you are. The so-called matter-antimatter dilemma is one of the most intriguing and enigmatic issues in contemporary physics. The intriguing subject of why matter and life evolved in the cosmos at all, rather than everything dissolving into a sea of energy, is at the heart of it, as is the existence of the universe itself. We must examine the ideas of matter and antimatter more closely in order to comprehend this. Atoms, electrons, protons, and neutrons are the building blocks that make up matter. Matter is the building block of anything with mass that occupies space, stars, planets, and living things. According to theory, each particle in matter may have an antiparticle. A positron is the positively charged counterpart of an electron. The proton has an antiproton that is negatively charged, and so on. These antiparticles are identical in mass but have opposing electric charges. According to scientists, when a particle collides with its antiparticle, they essentially cancel each other out, vanish, and release energy, which usually shows up as high-intensity radiation. The Big Bang should have produced matter and antimatter in precisely equal numbers, according to the mainstream model of physics. It would be illogical, from a physical standpoint, for one to have been preferred over the other, but reality tells us otherwise. The majority of the observable cosmos is made up of matter, with antimatter only occurring as particles in cosmic radiation or in contrived laboratory settings. Antimatter makes up no galaxy, no star, and no living thing. The great paradox is about to happen. After the Great Bang, matter and antimatter would have killed one another if they had generated in equal numbers. There would never have been a cosmos as we know it. Only radiation would have remained. Without atoms, light, structures, and life, the universe would have instantly vanished into void following the Big Bang if there hadn't been a tiny asymmetry or imbalance that resulted in the creation of slightly more matter than antimatter. Perhaps 1 particle per billion would have been sufficient to create everything we can see in the universe, including ourselves. However, what caused this deviation? Was it purely coincidental or part of a divine plan? In physics, a violation of the so-called charge is referred to as a CP violation. Symmetry and parity. This indicates that certain particles behave differently from their antiparticles. The current dominance of matter cannot be explained by such effects alone, even though they have been seen in experiments such as in the decay of some masons. This suggests that there must be additional explanations, such as previously unidentified processes or particles that slightly tip the cosmic balance in favor of matter. These, as yet undiscovered and unexplored, features are shown by the most recent findings and every issue in contemporary physics. Theories like leptogenesis and baryogenesis strive to link the matter-antimatter asymmetry to events that happened soon after the Big Bang. Other theories try to use alternative universes where antimatter predominates to explain the presence of matter. In the multiverse, this would represent a sort of cosmic balance. However, without any solid proof, all of these theories are still just conjecture. Therefore, the issue of matter-antimatter imbalance represents a fundamental gap in our knowledge of the universe's beginning rather than merely an unsolved subject in particle physics. Flaws in the conventional model of particle physics caused by baryogenesis and leptogenesis are like a cosmic enigma. Baryogenesis and leptogenesis are the results of following the hints of the magical imbalance in the universe. When baryogenesis and leptogenesis try to explain the minute imbalance between matter and antimatter, we delve far into the realm of particle physics to understand why. If matter and antimatter were formed in equal proportions during the Big Bang, there is essentially just matter left today. The production of an overabundance of baryons in the early cosmos is known as baryogenesis. Particles like protons and neutrons are called baryons. Theoretically, there must have been a period soon after the Big Bang when physical processes broke symmetry, producing a small excess of stuff. Going back to the alleged CP violation, the matter and antimatter exhibited somewhat distinct behaviors in specific circumstances. A tiny amount of matter might have survived in the end while the rest killed one another due to this slight asymmetry. This is closely associated with leptogenesis. Particles like electrons and neutrinos are called leptons. Very heavy right-handed nutrients are key to several ideas, such as seesaw mechanisms. These speculative particles might have caused an asymmetry in the leptons during the early universe's disintegration. Later, a baryon asymmetry was created from this lepton asymmetry. This involved, among other things, so-called Valeron processes, which are essential to the standard model of particle physics. Despite the mathematical consistency of both theories and their potential to address numerous issues, there is currently insufficient experimental proof. There are no obvious new sources of CP violation or the required heavy nutrients. In the upcoming 10 years, new research at CERN and the Large Hadron Collider in Geneva is anticipated to significantly advance neutrino research and resolve these particle physics issues. Perhaps then we will understand how the Big Bang's perfect balance led to the tiny imbalance that made everything possible, including the great cosmic balance and our antimatter universe's dark mirrors. What if there are other hidden universes besides ours where the main principle is antimatter rather than matter? Though it sounds like science fiction, this question is actually a fact of contemporary theoretical physics. The question of where the missing half went, that is, whether antimatter completely vanished or merely appeared elsewhere, inevitably comes up if the identical amount of matter and antimatter were generated during the Big Bang, the mirror. Universe theory is one intriguing theory. There are buildings in this anti-universe that resemble those in our own universe, but they are composed of antimatter. After the Great Bang, the universe would have split in two in such a scenario. The overall balance would not change if there were matter in our universe and antimatter in another, but the distribution would be different, and we would then have to accept that our world has an anti-imprint. If this anti-universe exists, it must somehow be connected to ours, and as science advances, we should be able to locate it. This theory is a symmetrical solution to the matter-antimatter problem and may also explain why some aspects of the universe, like the alignment of physical constants or specific gravitational anomalies, are so challenging to explain. The hypothesis even goes so far as to propose that dark matter, which is believed to account for about 85% of the universe's mass, is actually antimatter. Perhaps this is a sort of shifted reality, an antimatter world that interacts with ours just through gravity and is unaffected by any other forces rather than missing mass in the traditional sense. This would also explain why, despite the fact that dark matter's gravitational pull on galaxies and other massive objects in the universe is visible everywhere, we have not yet been able to directly detect it. These concepts are inherently tied to multiverse theories, which have gained popularity since the confusion in classical physics and are derived from quantum physics. If there are several worlds, each one might have its own set of physical laws that explain and counteract the dissonances in our own. If the missing pieces are discovered in our dimensions or universes, proportions of dark matter, antimatter, and other mysteries like the time paradox could be explained. The golden cosmic balance results when we consider everything at once. Once more, these are only theoretical considerations. Neither an anti-universe nor anti-matter dark matter have been demonstrated experimentally. Even assuming that a peculiar balance must exist could be a grave error. These unresolved issues demonstrate the extent of the knowledge gap that still exists regarding the universe and human beginnings. On the one hand, it appears that every scientific discovery and every solved enigma completes a map, but on the other hand, it also shows that entire nations and continents have been overlooked or not yet found on that map. Researchers may need to acknowledge that there are phenomena, other spaces, or forces within the known lands that are still poorly understood, or there may be dimensions beyond this map. Sign up for the channel now to regularly watch new videos.